Hey, everybody. Dave Lindbergh in Hong Kong with another episode of the THD Podcast. Got a little Paul's Boutique album cover going on this morning with the view out the window. So I hope everybody's having a good day. Today, we got a little bit of a remix. Speaking of Beastie Boys, we've got Simon Weston, who's normally our co-host. He's going to come on and he's going to tell us about a product he's been working on with his ZUMI Systems company. And it's called the CS-A86. So we'll get to that in a moment. But we also, to give some critical look at what Simon does, we brought in Colin, who's based in the Philippines. Colin Ward, how you doing today, Colin?
I'm doing good. How are you guys?
Good. Thank you for joining us to give us some third-party eyes on what Simon does. So we look a little bit, not biased. So Simon, the ZUMI Systems is, as we look at it from a high kind of marketing level, we call it the Swiss Army knife for audio engineers. So that is specifically related to this board, and just tell us what this board is, fait complete.
So what we're doing is it's building audio measurement instruments, and so the board that I'm showing here is built inside all of our products, and we're also presenting it as a standalone option. And the application would be you buy this board, an engineer uses this board as a plug-in, perhaps, or as a complete measurement tool for automatic testing or different test rigs. And so what it is the complete audio measurement instrument. So you have analog front-end processor that runs all of the measurement, sequencing and calculations and so on, Bluetooth transmitter and SD card storage and interfacing to other devices with digital communications, UART, GPIO pins and so on. So one of the points, just to be clear, because sometimes a bit of a misunderstanding, especially in the audio world, is it's not just an ADAC front end. So a lot of the times when you hear about, like a National Instruments measurement card, for example, it's actually just the ADAC front end. You still have a PC hanging off the end of that's running whatever application that does the FFTs and so on. You just get a raw, almost like a sound card, a raw data stream out of it. What we wanted to do is eliminate the PC completely. So the entire computational system, sequencing engine, and everything is built into the one device. So kind of a single board computer with that analog front end built in. And then that also gives you the opportunity or the ability to interface with all kinds of embedded devices, let's say with those UART, SPI, I2C type of interfaces, or just digital pins.
Okay.
So that's what we're looking at here, basically.
So as ZUMI Systems, you also build these into complete jigs or test fixtures or something, be it a headphone tester or some kind of speaker or driver tester. But in this particular application, you're targeting to build a computer for other engineers to use as the core in their test fixtures, or what's the target application for this? Exactly
that. Yep. So we actually use this as the core element of measurement fixtures. Let's say the headphone test device or earbud test device, things like that. But other engineers could buy this board and use it as a plug-in card into their ATE jig, for example. You have a bed of nails jig. You put your whatever device you're testing, maybe an electronics board or whatever, microphones or drivers, for example. Mm-hmm. Close the jig and run the test, and you'll make the frequency response measurements, all those audio-related measurements, do pass-fail criteria, etc., and as a standalone device, and with the data logging and so on. So this eliminates the computer. So it combines the computer and then maybe that peripheral test processing unit, like from another brand. It kind of combines those into a single unit. Okay. Yeah, exactly that. And so that's one of the things. See, I've been doing measurement equipment for quite a long time prior to developing this stuff. And you always have this nightmare. You have such a chain of equipment that you need. For example, measuring XYZ, you've got a PC there to run the main application. Then you'll have an external box, which is the acquisition front end. Call it a sound card, but I don't mean to demean these things. They're fantastic standalone devices. Then you may also have to have some other kind of USB to SPI converter or some other interfacing device. Then you're going to write code on your computer for running the communications to the device to set whatever parameters you want on it. Then you run some measurements and so on. So you have this really complicated chain of things you need to string together to get a measurement.
Would you say, just sorry to interrupt, but would you say as the average user, just for them to picture this in a simple kind of way, like quite often if you buy peripherals for your computer, when the Windows drivers update or Mac drivers update, it's complicated to get that thing to connect again because it's maybe a very specialized device where they don't update drivers every day. Is that a typical problem that people encounter with the audio testing peripherals that are
exactly that? I guess so. Windows is not too bad, but yes, you definitely have this problem where not only are you trying to maintain a measurement equipment, now you've got to worry about the Windows operating system. So you might have to call the IT guy to come and fix some Windows-related problem and so on. So we just get around all of that. It's more of the ilk of an oscilloscope. So I always used to see the electronics engineers. They'd have an oscilloscope on their desk and they can do whatever, probe around their board. And then us audio guys, we have to go down to the lab, switch on the computer, plug in 16 different connectors and so just to get a sweep out of something.
So exactly, I was going to ask you exactly that. As a development engineer, here's my oscilloscope on right behind me.
Yeah.
Do you think you can apply this as a bench tool in the kind of audio precision type environment where can it do the generation too, as well as the measurement? I mean, can I use it?
Sure, absolutely. Of course, I should mention that. Yeah, it generates all the output signals and the input signals.
Right.
So,
we can apply it in a similar way to a tool like AP for.
Yeah, and I think we'll put something like that out fairly soon. That is a small benchtop unit. It's essentially taking this and just housing it, really. Right. And I think we will do that very shortly. But just in this case, what we're presenting is an engineer buys this. And so, okay, now what's the use case then? I'll jump ahead to that. One of the things, let's say you're developing a particular product and ANC is a big one. So in an ANC product, you'll have filters, your feed forward filter, feedback filter, you might have an EQ for it, and you might be running over Bluetooth. So you're developing an electronics board with multiple channels, multiple pathways, for which you're very interested to make sure the frequency response of those pathways is very correct. And so it's quite a laborious task to go around and measure all the different frequency responses, collect that data and so on. Whereas what you could do is buy one of these boards, you make yourself a little bit of nails pin jig, and in one press, you measure all of those paths. And so you get a complete characterization of your thing in one shot, as well as being able to, of course, communicate to that board at sort of MCU level to switch on this function, switch off that function, give me this input, give me that output.
Okay.
And then you get that all self-contained into one unit. And during development, you plug it in and measure your board. You can find problems very quickly, save an enormous amount of time, and collect all of that functionality into one package.
So it could be used for like any kind of audio path electronics or systems. So you can take that core board and build it for testing all kinds of scale of devices, whether it's subcomponent or complete headphone system, for example.
Yep, exactly right. So the firmware in it has a sequencing engine, and the ability you're actually based around making measurements, doing actions. That means to set pins or interface with other devices, do pass-fail checking, quality control checking, log that data, and you also have, in the sequencing, you have a decision tree. So, for example, I make a measurement. If it doesn't meet the criteria that I'm after, do something and repeat their measurement. So you can have this iterative process, and that's actually used for ANC production trimming too.
Okay.
So I'll jump over. I can put that here. There's also a display panel module that goes with it. So that is plugged onto this board. And this, for example, I mean, we provide this display module. So this also does drives the LCD display. It's one specific controller driven over SPI, as it happens, which I think is called the ILI 9488 LCD display. So that provides some UI stuff. Now all of these pins have been set to certain functions on the board, you see. Now you might say, I don't want that display board. I'm going to use this as a client plugged onto another motherboard that's controlling the test. And I just want to instruct this to measure some characteristic, give me the data back. Or alternatively, you can use this type of setup where this is the entire brains of the system, and it will do the communication to the DUT to do configure X, Y, or Z.
Right, so you can use it as a slave measurement system, right? And
yeah, slave or a host is I guess the point that you can say.
Is there some kind of API that lets us use that? Or how does that work?
Yep. Okay. So you have a serial command interface. Actually, I'll show you that. So Bluetooth built in, by the way, and I can use this. We don't actually have an app, but this is a Android app. It's from the Arduino family of stuff, and it's going to send serial commands to this over Bluetooth. So I'll jump in and I'll connect through RF-COM, and it's all ready to go, obviously. And so now this is sort of like the host for the board, and I can I'm just using the D-pad controls or start or stop measurement kind of things. So that would simulate the effect that you could have either by connecting through physical UART wires or by Bluetooth SPP, which is effectively the same thing as sending serial commands.
Sure. Yeah.
So a host would be communicating it with like that, and in the host, you take a look at the list of commands: start, stop the test, wait for something. And there's a range of stuff. So what I'll do, I'll jump in if you don't mind, then, and just show one use case. So this is the AMS Anc Evaluation Board.
Okay.
For your not digital filters, it's an analog filter system. The principle's identical if it's a digital filter system too. This one just happens to be publicly available, so it's not an NDA type of job. So the chip on the AMS chip is configured via I2C, and you set various input, the input mux, a gain of microphones, and a system register if you want single-ended output or differential output, and so on. So I'm plugged into this header, happens to have the I2C on it. I've got the I2C on this board also, and let's just jump in and scan that I2C bus. I don't know if you can see that. And we've got one device on the bus at OX46. Now, of course, that's what that chip is. So nothing too fancy about that. We do have an AMS ANC module in the firmware. So essentially what that means is the register map of that chip is built in, having to be a popular device. Not so much anymore because they're moving on to a newer system, but that's there anyway. And we can read out all the registers and so on for that chip. And that would be part of the measurement process too, is to look at the configuration of that chip. So next, what we'd be doing is saying we want to measure the audio line in path from input socket, which happens to be this one right here, out through the headphone speakers, and we might have an EQ function for that. So I'll put that one into perhaps, I think it might be that output there. I can't remember. We'll soon find out. And then I'm going to take the outputs from the headphone jack here, and I think we'll plug that one into.
So these signals you're plugging in now, Simon, they're analog signals, right?
Yep. It's all analog. Yep. Right. So I've got headers. We've got all the headers here. So there's 2 output ports. You can switch between 2 output ports. Each port has a left and a right. So 2 pairs. Then I have a header with 4 analog input channels, and I've got a header for the digital I/O or UART, I2C, etc. So you just configure that to whatever you want. Essentially, if we instruct it to do an I2C communication, it will put those pins to I2C mode. So what do we do? And we'll take the output out of the headphone. So let's quickly just run that and see what happens. I'll find out pretty quickly if I've got the connections right. So I have so far, and it turns out that the line in is a completely flat line because there's no EQ on it. What's more interesting will be to take a look at the other paths. So there's a sequence of measurements going on where we tell the chip to switch off the ANC filter part of it and just run a signal from line in out through the headphone socket. Then next we'll say switch on the ANC part, and we're going to put our signal in on the microphone pins of that chip to simulate the microphone signal coming into the ANC filters. And we'll say that they have 2 filters as it happens, 2 stages. We'll say switch off the second stage. I just want to see the first. In fact, the step before that, I want to see the path from this microphone input to the output of the device's microphone preamp. Then we'll put the first stage of filter, then we'll put the second stage of filter. So as we go through each process, we just switch the mux on that device, and therefore we can very quickly see if we have any mistakes and whereabouts that mistake arrives, when you're doing hand soldering or development kind of thing. Mm-hmm. So we'll see what we get for that. Each time that flashes, just jumping to the next step. So we'll just put that there. This one happens to be the line in, which said is a flat line. But if I got mic is dead, I've got something wrong there maybe. And amp is noise 2. Let me have a quick look, see what have we got going on here. Nope, and maybe we need to just pull that for a second. That sometimes that bus can get locked up. I'm not getting a signal out of that. I plugged myself in the wrong ports. I don't think so. Let's quickly just take another look at the bus. No, I see it is. So this AMS chip is a bit finicky actually because it has the ability to be either address. You can reverse the data and clock pins. I think we might need to just like that. Or maybe I'll try it the other way. I might have the data and clock around the wrong way. Can't seem to get it to scan that bus nicely anymore.
Yeah.
Let's have a look, see.
Engineering, right? These things happen.
Bit of quick debugging, if you don't mind.
Yeah, no problem. This is real engineering.
So I'm scanning the bus and it's actually responding with all addresses. I've come across this in the past. If I disconnect my I2C, there's nothing on the bus. I do connect it. Yeah, it's still representing all of those addresses. Let's see, what have we got going here? We might have to skip this bit and move on. So keep going with the questions while I play with this anyways. And
yeah, so from a development engineer's perspective, particularly, like developing audio amplifiers and stuff, what kind of measurement accuracy do you think you can get? Right? So if I'm doing a hi-fi amplifier, how low can I go on distortion measurements and things like that?
So distortion, you'll go down to about 0.01%. It's an 18-bit ADAC. So it gives you about 100 dB signal to noise ratio.
Right. So is there scope for if to extend that to a 24-bit ADAC or something?
There is. It happens that the analog, the ADAC that we're using is an 8-channel simultaneous sampling.
Right.
And you drive the sampling yourself. It's not clocking at a fixed rate.
Right.
So a lot of the audio chips that you'll get will be 2-channel, and you get 24-bit variants.
Right.
But they're clocked at fixed rates, so it's a slightly different architecture.
Okay.
And in this format, there isn't really anything available in 24-bit that will do. And so again, the point being that 8-channel simultaneous sampling, rather than being a lot of the 24-bit ones will actually be a sequential sampling. It's very quick, so that you don't see a big phase difference between channels or anything like that. But it's not necessarily simultaneous sampling. But it's a very high performance chip. Okay, it's 18-bit, not the 24, but there's very few applications where you actually need that extra resolution, essentially. Especially in a lot of audio stuff when you're dealing with dB scales. So, of course, if you're doing electronics and you're trying to measure a noise floor, yeah, maybe you could do with the additional resolution. I mean, a lot of scopes will be maybe just 12-bit.
Sure. I mean, my scope is 8-bit, so it's particularly useless for making things like FFT measurements and so on.
Right. Yeah.
Even though it has the feature. But yeah, for an audio amplifier, I'd probably needing to measure. If I was doing a high-end one, I'd be trying to measure, signal to noise. I'd be looking for 110 dB, something like that.
Right. Yep.
So anyway, just a question.
There is always scope for that, but what we're targeting is not exactly that application, right, which tends to be
the core computational firmware would still be applicable. It's just a question of getting the front end measurement system higher res.
Yeah, exactly right. Yeah. I'm going to flip this back. I'm still trying to get this thing to respond but the bus has apparently locked up on this. Yeah, there's my battery dead or something like that. We might have to table that one for the moment and just move on.
Okay.
So I'll explain a couple more things. So it includes a lithium-ion power management chip, battery charger, power management chip. So what I have here is actually running off battery. And I guess that's another point about the architecture. It's very low power consumption.
Okay.
So, from a small headphone size lithium battery, you'll get, maybe 4 or 5 hours of measurement at full blast. And so that can be a very, very beneficial thing compared to needing to have an external power supply. But setting those constraints around power consumption changes your choice of componentry, basically, because you don't have, a mains unlimited power supply. So you're thinking about things that work very efficiently too.
So what would be the pros and cons for people for the portability aspects in a test or R&D situation? Is it just because it is that kind of portable tool they take with them, or?
I don't know if you would think the same thing, Colin, but if you have a device, let's say you build yourself, you're working on a project, you build a small fixture with a board inside, it's running all your measurements for you and has a battery built into it. If you have the ability just to walk over to the soldering desk with that, or move around, and you don't have to drag the DC cable around, things like that, it's such a massive benefit. It
really is. It's very useful. So I can see the application there. Sure.
So it's something the purchasing people wouldn't find interesting, but the people that actually use it, they love it.
Yep, of course. And then if you're doing something that makes it have a degree of portability, so if you're building a certain audio product PCB, you make yourself a small fixture, you can give that to a QC operator to put in their bag, go to the factory, pick out a couple of boards and make those measurements.
QC release inspection and stuff like that. If we for end brand customers, when they get the product, they can do their own verification testing. Inbound product, pretty good.
Right. Okay.
It's a Bluetooth transmitter as well. So it acts as the A2DP source and HFP audio gateway. So it's like the smartphone side of the Bluetooth chain. Okay. So of course you can measure through a Bluetooth system as well. Output your test signal through the Bluetooth and measure the results coming back from the speaker outputs or whatever it may be.
Okay.
We've got a bunch of EEPROM built in. So when you set up a test configuration, it's stored on the EEPROM. It's not volatile. It stays forever.
Okay.
And then you have that, so you don't have to concern about reloading some file each time you want to use it. It stays in that state.
Okay.
Forever. So that's that kind of like a program it and set it and forget it approach. For mass storage, we just use an SD card as essentially as a disk drive, and so you store your log files to SD card.
Right? It logs the test results on the SD card, right? So you can do later analysis or whatever of those, right?
Yep. So we do logging. Then in terms of logging, we do two things. One is we call it information log or a summary log of the test. They'll tell you the time, how long the test took, what the result of each pass-fail criteria is, and whatever some single number levels, the RMS inputs, output levels that we got. Then there's the full data log, which is the frequency response curves as strings of frequency points, magnitude and phase points. So in some instances, you may not want to store an enormous amount of data, which can be large. In those cases, you would just store that information file instead.
Okay. Is there other ways to port the data besides SD card? If somebody wanted.
Okay, so then yes, you get all the data out through the UART as well, either over Bluetooth or by USB into a PC. So if you wanted to hook something up and log it, you can send all your data on those paths. Just give me 1 second, guys, because I'm going to have to plug in this computer. The battery's almost rinsed.
All right. Running into all kinds of technical things today. All right. And so, yeah, you got the system working now, Simon, so you could show us a demo?
So we had a brief intermission. So now I'll just run through and we get that same flat line. This may not be very, very clear. And then for the filters, we see actually this is a filter functions designed for one particular headphone, I believe. And then we get those the curves of each stage of the filter. So what I want to demonstrate next is what do we do with pass-fail type of things. So a menu. All of these things could be done by other means through this menu interface or directly by commands, of course. I'll just use the menu interface. And I'll just use the convenient function, which is to set the bounds from the current measured data, and it generates a set of limit curves around all of those response measurements. So this would be the case where you take a golden sample unit and make that measurement and then set that as your reference for your ideal measurement. And so away we go, we'll measure the same thing again, see what we get. And the green lights come on, we get a pass result for that. Let me see, maybe if I'll pull one channel, let's say, so something's wrong condition.
Okay.
And the red lights come on, we get a fail essentially. So in this case, the a GPIO pin is signaling the fail result, is causing those LEDs to switch on. You might have a host system that takes that digital signal, high and low for pass or fail type of a thing. Or you send a whole that comes out over the UART and the command in terms of what that result is. If you had a more advanced system that can interpret character strings, for example.
Okay.
And then all the while, all of these measurements, if we so choose, have been stored onto the SD card. So like I say, we can go back later and run those through various sort of analysis programs.
Okay. So this is kind of a brief look at how it could be used with the AMS chip for ANC measurement. Is that just a quick
exactly?
summary?
It's essentially just to show that we have multiple output paths and multiple input paths, and we can control that DUT via I2C. The same would apply for other SPI or UART. I2C is fairly common.
Okay.
Yeah.
Anything you want to ask there, Colin, about that?
No, I think that's pretty clear.
Okay. And so these devices, they're built in Japan, is that correct?
Yep, they're built in Japan. So in fact, the boards assembly are done in other parts of the world, but
okay.
That's
I have fixturing for the DUT. You can do custom fixturing.
I didn't catch the beginning of that. Sorry, Colin.
Sorry, so for test fixturing for the device under test, you can do custom fixturing for that.
Yep, we certainly could do, most certainly. But I just wanted to try and promote this as an engineer's tool where they would use it for their own fixture builds in this instance. Yeah.
Okay, so you supply that bit of kit and you supply the support to help them design it into a
exactly
fixture.
Right. Yep.
That's the nut of the business. So I guess this is a kind of a good snapshot. Everybody's wondering who the F is this Simon guy on these podcasts, and how does he know so much about headphones and ANC? It's because this is what he does for a day-to-day in terms of developing this this test and measurement company. Is I guess the best way to explain it. Okay, great.
See, if someone in a company doing a specific type of product, you might actually, over a period of time, refine your own test fixtures based on the class of product that you're using. So you'll have one aspect would be the pin jig interface. Mm-hmm. And you know what I mean? And those things, there's a lot of companies that will just build those very easily for you. Then another facet would be the sets of tests that you want to perform. And so what we want to do is provide the solution for that element of it in this case, which is to say you have a solution to get all of the measurement results that you want for any given device without having to go through and code a lot of script yourself or, connect up large chains of equipment, essentially.
So developing those measurements, is there? We talked earlier. You said you had an API, right? Is there also like a drag drop tool to make the test programs you want?
Not at this moment, but definitely people are asking about a nice GUI to do that stuff. It's not a huge thing, so we have a PC app too. I'm not set up to show that right now, but you can get all the graphical display, etc., through a PC application.
Okay.
What we actually are using is it's like an any file structure, and it's just a list of key and values. So, for example, you get a little bit of experience for it. It's very intuitive and simple, and probably a lot faster than trying to play with a GUI. Once you understand these things, so you would just write the output signal. I want a chirp. On the inputs, I want input 1. I'm going to call it a name. Input 2, you give that a name, and I want to compute input 1 divided by input 2. Right. These type of things. Now you can do that through a GUI for sure, but when you write it directly into an any file, can be very simple. Yeah. So, but that's not really a big issue. So quite often we'll just do that for the customer. They just say, I want to do X, Y, Z, and it takes just 2 minutes to write out those list of instructions.
Okay, very good. So yeah, I think the pointing to the fact it could be on a larger monitor people watching the video will understand.
Sure. Okay. Well, this
about.
is just to this is a small UI board that gives you some buttons and a small display for convenience. But if you want a larger display, then you would use another device. So you could run the UART, for example, to a Raspberry Pi, and then run a monitor off that with take that data stream off the UART and put it into a graph. We don't have a graphical processor built into it.
Sure.
It's enough grunt to drive a small LCD display, but we're not going to do an HDMI output.
Sure.
So strategically, or philosophically, we're not going to make a graphical device here.
That
element of it is offloaded to either Android tablet, PC, or whatever it may be.
Yeah, so it's
because once you start getting into that graphical processing, you're talking about quite a lot of power consumption.
Yeah,
and it's really heavy, really fast. So
it's not the focus of the business either. So
that's right. That's right.
I get your strategy here. Okay.
Yeah.
All right. So anything else you'd like to add, Simon?
No, I think I just covered pretty much the basics of what I wanted to get through.
Okay. So Colin, thanks for.
Yeah,
thanks for chiming in today, and of course, everybody, anybody wants to comment on it, we look for your comments and like and subscribe, and all that jazz. And we'll catch you on the next one. Thanks, everybody.
Thank you.
Bye.